Good morning, good afternoon, good evening, everybody, wherever you might be. It is my great honor and pleasure to welcome Jack Spielberg from Arizona State University. He will report on his joint work with Ian Mitcher, and it's going to be on AF algebras associated to oriented combinatorial data. The floor, the Zoom, the internet is yours. Take it away.
Luckily, there still is a floor. Thanks, Piotr, and thanks for inviting me to give a talk in your seminar.
Our pleasure.
And as you mentioned, this is joint work with Ian Mitcher. So for a while, I've been interested in this construction of C-star algebras from what I call oriented combinatorial data. And really, it began with graph algebras. So a graph is an example of what I would call oriented combinatorial data. So a directed graph is just a bunch of dots and arrows. So here's a typical example. And I always felt this was one of the reasons why this construction was so popular, so useful, is that any diagram of dots and arrows is a directed graph. And then there's a way of building a C-star algebra from that information that produces many interesting C-star algebras. So since many talks have been given about graph algebras, especially in this seminar, let me point out that I'm following the Australian convention. So paths run in the opposite direction than you might expect. And the reason for this is really, I like to think of a graph as a directed graph is really a small category. So that arrows really represent morphisms. And when you compose morphisms, now of course it's all wrapped up with the way we are used to writing from left to right. Mm-hmm. So here I indicate that, hey, I've got a laser pointer. Ooh. So if you have a sequence of edges like this one, so we say F1, F2, F3, F4, really we should think of these as functions. That really means F4 followed by F3, followed by F2, followed by F1. So as a composition, it looks like this. So the path I'm describing, if we write it this way, we should follow it this way.
So it's not just because the Coriolis force is opposite in the southern hemisphere?
I believe that's not the case.
Okay.
I think it's because Alex Kumjian is an intermediary between the northern and southern hemispheres.
I see.
Okay, so really I think it was Kunz and Krieger who taught us how to associate C-star algebras to directed graphs. And then their construction was generalized really to arbitrary graphs in many different ways. And of course, this began with Kunz's algebras that came from the simplest graphs, just some loops with a single vertex. And that is really why this became so important, is such remarkable C-star algebras had this origin in this directed graph. In particular, every AF algebra is at least Morita equivalent to a graph C-star algebra. And one of the successes of graph C-star algebras that's often cited is that it's easy to characterize when the C-star algebra of a directed graph is approximately finite dimensional. So it has to do with whether there are cycles in the graph. So the theorem is that the C-star algebra is AF if and only if the graph has no cycles. Let's just come back to the picture for a moment. We have a cycle here, F3, F4, F5, because you can go round and round and round. Another cycle is the single loop F1. Right? So you might say there are two cycles in this graph. It was noticed that the Kunz algebras, of course, are built with isometries, and the presence of isometries is detected from the graph by whether or not there's a cycle that has an entrance. Okay, so and let's not define entrances. Let's just say that it's pretty clear that the cycle F1 has an entrance because we can get into it by following F2. Whereas this cycle has no entrance because there's no way to get into it. If you're in it, you're in it. If you're not in it, you can't move toward it. So having a cycle with an entrance turns out to be what gives you an infinite C-star algebra. So it's remarkable how tightly the properties of the graph control properties of the C-star algebra. Okay, now the point of view I like to take is that we should really think of the graph as giving us a set of paths, finite directed paths. So if E is the graph, I let E, this is fairly standard, E star denotes all the finite directed paths. And we should think of this as a small category. So this is the quintessential example of a small category. What is a small category? It's really just an algebraic structure like group or monoid or ring, except that there's possibly more than one unit. So a monoid is a structure with a associative bilinear operation and a unit. And a small category is just a monoid with several units. So a homomorphism from this, well, so the vertices would be the units, right? And the paths are the morphisms in a directed graph. I think this was Alex's brilliant observation. The length of a path is a homomorphism from this small category into the natural numbers. And this length homomorphism has the unique factorization property. So I don't want to dwell on the unique factorization property, but Alex and David Pask generalized the idea of directed graphs by, well, what do? You have a small category, but you should have a homomorphism into k dimensions instead of one dimension. So a homomorphism to nk still having this unique factorization property. And they called such things higher rank graphs, or a k graph if it goes into nk. And then they define C-star algebras very much like the process of defining them from directed graphs. So the higher rank graphs are a more complicated kind of oriented combinatorial data that gives rise to a C-star algebra. Higher rank graphs are very complicated. Building a higher rank graph, you have to ensure that there exists this homomorphism having the unique factorization property, and it's really quite complicated. But there are many beautiful results about higher rank graphs. And of course, people wanted to try to prove the same kinds of theorems that they had for directed graphs. And in particular, I think it's still an open question when the C-star algebra of a higher rank graph is approximately finite dimensional. So Gwian Evans and Aidan Sims made a detailed analysis of this problem. It's just really hard. So they had a lot of results, but they didn't completely finish it. And I think it's still not known what is a necessary and sufficient condition for the AF property for higher rank graph C-star algebras. But they do give a very beautiful necessary condition. It's the absence not of cycles, but of generalized cycles. So in a higher rank graph, the situation is a little bit more interesting. Let's start with a bit of notation. I'm going to use Exel's notation, this double intersection, to mean that two elements have a common extension. So I write this.
How do you do this symbol in LaTeX?
You can, it seems there's like books of symbols in LaTeX. Yes, I could just write cap with a capital C and you get this one.
Wow, okay, thank you.
So I'm writing this mu lambda for all compositions mu nu, where nu is in lambda, something like that. So, well, mu, anyway, so this intersection represents all the common extensions of mu and nu. And if there exists a common extension, we say that mu and nu meet. And I use that funny intersection symbol for that. So what is a generalized cycle? So you have a pair of paths or elements of the category with the same source, the same range, and such that every extension of mu meets nu, or you might say nu meets every extension of mu. So mu somehow can't get away from nu in this sense. Now, of course, this is an asymmetric relation. If it's true the other way around, well, that's okay. But if it's not true in the other order, then we call it a generalized cycle with an entrance. And Evans and Sim showed these two facts, that the presence of any generalized cycle means you don't have an AF algebra. And if you have a generalized cycle with an entrance, then the C-star algebra is infinite. Okay, now these are not necessary conditions. They're sufficient. Well, they're one-way streets, right? So in fact, Mitchell showed that the converse of one is not valid. So he has an example of a higher rank graph with a generalized cycle, no generalized cycle, but non-trivial K1. Okay, but they also give these beautiful and complicated examples that just have no detectable obstruction to being AF, except that it doesn't seem to be easy to prove that they're AF. So the whole situation with higher rank graphs is very mysterious. When is such a thing giving you an AF C-star algebra? So Ian and I were trying to understand this, and we decided that we would relax the requirements of higher rank graphs. That somehow makes it so hard to study. So if you look at a higher rank graph from far off and squinting, so all you see is the most basic structure. What is it? It's a directed graph. Now, some people draw different edges with different colors, but basically it's a directed graph, but some paths have been identified. So it's a directed graph with identifications. And the tricky part of building such a thing is to arrange the identifications so that you get this degree functor. But you don't need the degree functor to build the C-star algebra. In fact, all that you need to build a C-star algebra is a small category with left cancellation. So Xin Li has done a huge amount of work. Well, he pointed out that if you have a monoid, it's the left cancellation that allows you to build a C-star algebra. And Rui Exel, I think, was the first person to point out that for higher rank graphs, you don't really need the degree functor. The C-star algebra somehow comes about directly from the left cancellative category, small category. So I'm going to assume a little bit more. So here's the definition of what I call a category of paths. So a small category that's cancellative on both sides, and no non-units have inverses. The idea is that when you concatenate two paths, it should get longer, so you shouldn't be allowed to cancel. So it's a naive sense, but this is asking for much less than a higher rank graph. Let's see. Yeah, now, so how do you build a category of paths? So building a directed graph and identifying paths, it's a lot like defining a group or a monoid by generators and relations. So it might be that you over-identify things and everything collapses to nothing. So one way to get a category of paths that's not trivial is by what I call amalgamation. So if you have some categories of paths already, you can glue them together along the units, basically in any way you like, and get something else. So you can start with higher rank graphs. Some of them can be defined without too much trouble. And if you start gluing them together, you get things that aren't higher rank graphs, but are still in this setting. Okay, so I've talked a lot about how you just need this question.
May I ask a question?
Yeah, go ahead. Yeah.
So like dropping the degree functor, how do you build in like the Kreuzer relation? I mean, like usually I would the way I think about the degree function playing a role is like dividing up your edges, right? And saying which edges contribute to one set of consecutive relations while another set.
Yeah. So it comes down to the minimal common extensions. Actually, I'm going to discuss it a little bit in a few minutes.
Okay. Yeah. Thanks.
Yeah. So maybe this is this slide actually is part of the answer to your question. The most natural way of defining a C-star algebra is to build a topological space from the paths in the small category. And this can be done in a very natural way, as I'll indicate in a moment. And then this becomes the unit space of a groupoid, and that's also in a very natural way. And then from this groupoid, we build a C-star algebra, and that's where you get a C-star algebra. So you don't, well, it's not clear what generators and relations you ought to use from this small category. Though of course you could just write down what look like reasonable generators and relations and see if they work. But the process of building a groupoid somehow comes intrinsically from the small category. And after the fact, it's possible to give a description by generators and relations. And it turns out that they're essentially identical to the generators and relations that are given for higher rank graph C-star algebras. So it gives a kind of different way of producing the C-star algebra from the original data that doesn't feel like we're just making up some generators and relations that seem to be convenient. Okay, let me talk a little bit about how this happens. So let me introduce some terminology and reiterate a bit more. So if we have a category of paths, capital lambda, I let lambda 0 be the unit space, and S and R are the source and range maps. And here I'm again writing this notation we have. You know, if you stick an element of the category next to the category, you're talking about all compositions that make sense. And we talk about extensions in this way, the same as before. So if mu is an extension of lambda, that means lambda is an initial segment of mu. And it's convenient to have a notation for the initial segments of all the initial segments of a given element. So as I mentioned before, in the context of higher rank graphs, the intersection of lambda lambda and mu lambda is the set of all common extensions. And if it's not empty, we say that the two paths meet. Otherwise, they're disjoint, and I use just perpendicular symbol for that. Okay. Now, even in the case of higher rank graphs, this is a very general class, and there was an important simplifying assumption given by Rayburn, Sims, and Yiend called finite alignment. So they gave this for higher rank graphs, but the same definition makes sense for categories of paths. So we say that the category is finitely aligned if given any two elements, lambda and mu, there's a finite subset of lambda, so that all common extensions of lambda and mu are extensions of one of the elements eta from the set F. And then there must be a unique minimal such set F of elements eta. Those are the minimal common extensions of lambda and mu. So any two elements have a finite set of minimal common extensions. Every common extension extends some minimal common extension. Of course, if the two elements we started with are disjoint, then the set F would have to be the empty set.
Can I stop you here for a second, Jack?
Yes.
I'd like to get some intuition. It's a pity you are not drawing some pictures.
Yeah, they'll come, or some pictures.
They'll come,
it's
okay.
not so easy. And anyway,
when you say that you have a common extension, should I think that I have, say, two paths, and that finally at least one vertex, I'm thinking still in k equal to 1. Okay, I know it's about higher rank graphs, but in particular, 1 is also a good natural number. So if I would have that, I have two paths that they meet finally they meet at one vertex, can I call it as having a common extension?
So let me try to draw a picture. Okay, so here's the way I think about it.
Mm-hmm.
So here are two paths with the same range.
Yes.
So a common extension means that you can fill in the rectangle this way. Say this is C and eta, so that mu
So
C
you extend it
equals
backward.
nu eta. Yeah, because this is the convention about composition of functions. So it's the opposite of what you might be used to with directed graphs if you use the original,
Yeah,
or the
yeah.
earlier, the non-Australian convention on that.
Yeah.
This is the idea of a common extension. So that these are four distinct paths possibly, and it's only when you do this composition that you get the equality here. So then so this path is the common extension of mu and nu.
Yeah. Okay. Thank you so much. This really helped me.
You're welcome. Yeah. No, I never quite know what's going to be the right thing to put down. Let's get rid of this. Okay. So I said that the first thing to do is to build the unit space of the groupoid we want. So it should be a locally compact Hausdorff space. So here's how we do. We start with a finitely aligned category. That's why this is a fairly straightforward definition. So I'll call the subset little x in lambda directed if given any pair of elements in the set X, there's a common extension of those elements that's also inside of X. So X contains a common extension of any pair of its elements. So that's a kind of directed property. If you think of moving arrows backwards, it means any two paths in this set eventually can meet up somewhere behind, staying inside the set. And the hereditary property is closing it up under initial segments. Now, if you have such a set, all the elements in the set have a common range, so we can extend the range to these directed hereditary subsets. And we let lambda star be the collection of all directed hereditary subsets. And within there, we have the notion of a cylinder set. So all x's that contain the element lambda form a cylinder set defined by lambda. And then you can prove, and again, once you've decided this is the thing to do, it's not hard to write out these details. The set of all these generalized cylinder sets generates a totally disconnected, locally compact Hausdorff topology on the collection of all directed hereditary sets. And in this topology, the cylinder sets are compact open sets. So it's this collection lambda star that becomes our space where we can define a groupoid. Now within there, we can look at the maximal directed hereditary sets with respect to inclusion. So I just call that lambda double star. And then the boundary of lambda is the closure of the maximal elements. And this is completely standard. So many, many people have done this same kind of construction in similar contexts. You know, the boundary should be the closure of the maximal elements. So for example, if you have a directed graph, then lambda would be the set of finite paths in the directed graph. So the directed hereditary sets can be identified with all finite and infinite directed paths in the graph. But the boundary consists only of the infinite paths and the singular vertices, the ones that receive either no or infinitely many edges. So if you're used to directed graphs and you turn the arrows around, you'll recognize this idea. Okay, now the important thing is that from this category, we get dynamics on the boundary. Oh, in fact, we get dynamics in the whole set of lambda star of directed hereditary sets. So these come from the following algebra of the category. So given an element in lambda, we can define what I call shift map. So tau lambda just means sticking lambda in front of an element. So it's defined on anything where the composition makes sense. And that's here's really where the left cancellation is so crucial. The fact that tau lambda is defined and one-to-one is coming from the left cancellation. So the inverse is also a bijection. And then these extend to partial homeomorphisms of this locally compact Hausdorff space, which we can define the same way. Our notation will be this. So just sticking lambda in front of a directed hereditary set means stick lambda in front of everything in the set and close it up under initial segments. So we get partial homeomorphisms of a locally compact Hausdorff space. It's not so hard to define a groupoid from this. Okay, so here's how we define the groupoid. So it's going to be a groupoid whose unit space is this lambda star. So we consider triples, mu nu x. So mu and nu should be from the category lambda, and x should be a directed hereditary subset of lambda. And the fiber product just means that the sources of mu and nu are the same and agree with the range of x. So the picture is like this. So mu and nu have the same source, and that's also the range of x. Now it's possible, maybe I could draw this. X might be really given by some eta followed by some y. Okay, so you'll have to forgive my handwriting because it's terrible. So y should belong to lambda star again, and eta, which I could maybe make look like an eta if I work. So if x is equal to eta y, then there's no reason why we couldn't use mu eta and nu eta as our first pair of coordinates, and then y as the last pair. So we want those triples to be equivalent. Shouldn't make any difference if we're dividing x, pulling off an initial segment of x and sticking it with the mu and nu. So we generate an equivalence relation using this idea. And then the groupoid is just a quotient by that equivalence relation. And we use square brackets for the equivalence classes. Multiplication, well, so you should have the matching coordinates here. And the idea, again, is, let's see. So here's, say, mu eta x, and maybe we have another one. Oh, sorry, I usually use mu and nu. And this might be eta. So the idea is we could really swap out nu for mu, swap out eta for nu. The result was to go from this one to this one, always with a final tail x. And we just interchange the beginnings to get an inverse. And the units are where we have really just a vertex as our paths. So it's really the unit space is identified with the lambda star. And we extend this bracket notation to allow a set in the third coordinate, so we can look at subsets of the groupoid. And then the theorem you can prove is that all these, if you let E be one of your basic sets in the topology on lambda star, then sets of this form give you a base for a topology, making this G of lambda into a groupoid. In fact, it's a tall groupoid, Hausdorff, and ample because the unit space is totally disconnected. And it's easy to check that the boundary of lambda is a closed invariant subset, so we could restrict to the boundary, and that would be the Kunz-Krieger algebra of lambda. Using the whole groupoid, we get the Toeplitz version. This is just a general setting where all the usual ideas from higher rank graphs make sense. So Alexander, this is the answer to your question on building the C-star algebras. There's no generators and relations in the picture at all. It's just coming from the algebraic structure of this small category.
Via a groupoid.
Sorry?
Via a groupoid, right?
Via a groupoid, yes. So remember, we had this notion of generalized cycles in higher rank graphs, but the exact same definition makes sense in this more general context. And you can still prove it's essentially the same proof. actually, I find many things are proved much more easily in this general context because there's less machinery to have to write down. So if you don't worry about the degree functor, then some facts which are still true become easier to prove because there's less machinery in the way. So if you have a generalized cycle with an entrance in this context of categories of paths, you still get an infinite C-star algebra. On the other hand, this is maybe too general. So Mitscher has examples with generalized cycles without an entrance, but are still AF. So the presence of a generalized cycle no longer precludes approximate finite dimensionality as it did before. Okay, now I want, okay, that's sort of like my introduction about categories of paths. And now I'd like to go to the work we've done trying to investigate the problems that Evans and Sim found, but by studying them in a more relaxed situation where you don't need to make such a complicated example in order to think about things. So we decided to look for the easiest way to build a category of paths that wasn't stupid and didn't have generalized cycles. So we could try to decide if it had to be F or not. So we build this by amalgamation. So we start with a 2 graph, which I draw here. So it's just a directed graph. I'm using the usual convention of giving different colors to the edges. So here's solid and dashed. So you could think of it as these two infinite sequences of paths, the solids and the dashed. And the identifications are a kind of commutation. So if you say follow alpha and then beta, it's the same as following a beta then an alpha. And the result is that every finite path, you can pull all of, say, all the alphas to the left side and the betas to the right. So every path has this form. Now, in general, you can start commuting things using this relation and write the alphas and betas in any order you like. Those are all representing the same element of the 2 graph. So a convenient way to write that is here, just indicate where it starts and how many alphas you're using and how many betas. So that's a typical finite path in this 2 graph. Okay, studying this 2 graph a little bit more, let's look at the directed hereditary subsets. So I guess I didn't mention this here, maybe I can now. So if you have any element of the category of paths, all the initial segments forms a directed hereditary set. So these are the finite directed hereditary sets. So the infinite directed hereditary sets come in 3 forms. So I'm listing them here. Right, so you have to have infinitely many edges. So you have to have either infinitely many edges labeled alpha or infinitely many labeled beta. You might have finitely many of the other kind or infinitely many of both. There are only countably many infinite elements. On the other hand, the boundary, oops, I forgot that I'm not laser pointing anymore. The boundary is just the those that use infinitely many of both. Now, very important for our examples is this fact here. So what am I doing here? So this triple is an element in the groupoid, and it's actually an open point in the boundary. Right? The boundary is just countable. So its characteristic function is a continuous function of compact support in the groupoid. So it represents an element of the C-star algebra. And in fact, it's a unitary if you restrict to just this subset BM lambda, boundary lambda 1. And I've written out the main point here is that it has the same source as range. So the source would be beta alpha infinity, beta infinity. So this one, but of course, that just is still infinitely many betas. but we could pull out alpha instead if we like and get the range of that thing. So here's an element with the same range and source, but it's not a unit. So this is indicating non-trivial isotropy in this 2 graph. And sure enough, the C-star algebra of this 2 graph is just the stabilized continuous functions on the circle. Okay, so I said we're going to amalgamate to build our examples. So this is the first ingredient, is this 2 graph. The second ingredient is a 1 graph or a directed graph. And I'm using the same set of vertices to indicate how the amalgamation will go. And the idea is that between successive vertices, we have a certain finite number of edges. So the sequence K1, K2 is just representing how many edges you have between the K plus first and the I plus first and ith vertices. So this is supposed to be self-explanatory, this picture of a 1 graph. The notation's a little awkward, right? So the subscript on gamma tells us where it is. And the superscript tells us which one of the edges between those 2 vertices we've got. So what we're going to do is take these 2 examples on the vertices V1, V2, V3, and just glue them together along those vertices. So the effect is like salting in these edges labeled gamma amongst the commuting alpha and beta edges from the 2 graph. So here's the picture. It's a bunch of Easter eggs. You know. So here I've reverted to the coloring of edges in the 2 graph. But you should realize this is not a higher rank graph, right? There's no commutation between anything involving a gamma. So there's no identifications of edges that involve gammas, paths that involve gammas in them. So the idea is that, say, any combination of alpha 1, alpha 2, beta 1, beta 2, if we follow it with gamma 3, it's blocked from whatever comes afterwards. And because of this, it's easy to observe that this, well, it's a category of paths, and it has no generalized cycles. So these are the examples we like to study and try to figure out what the C-star algebra is. So what's happening now is I'm going to try to show you how you build a C-star algebra from a category of paths in this explicit example.
Sorry, Jack, since we have pictures, could you draw a nice picture of a generalized cycle?
There are no,
yeah, there are no here, but I want to see what I want to see what is lacking here.
Yeah, so I think it's just not so convenient to draw such a thing. It's a little, I find it awkward to draw these things. Because you're, well, so first of all, you have identification of sources and ranges, and you have to say which paths are identified with which, and you can't see from the picture which ones they are. So you have to write many things down. But let's see, so what the idea here is that if you have, say, 2 paths between V1 and V3 that are different, okay? Then if you follow one of them with gamma 3, then nothing that comes after that can possibly affect what you did before. So you can't possibly get something that matches your other path in the first 2 slots, because nothing that comes afterwards can get past this gamma 3 to influence what happened before. And that's why, given any 2 paths, if you take the first one and follow by gamma 3, it will be disjoint from the other path you had of length 2.
Why disjoint? I mean,
in the sense that they have no common extension, right? So any extension of your first path, its
will contain gamma 3.
Rank 2 is fixed, and so it can't possibly match your other path here, and hence can't extend it.
Okay.
Well, you know, I'm sorry, I'm not able really to give a very clear picture of this one. Okay, so yeah, Guillen's comment is apt. I mean, of course the 2 graph does have generalized cycles, you know, with entrances. Now, without entrances, right? But those are blocked by using the 1 graph edges. So we break those in this way. Yeah, and I think your example is a good one. If you just take say alpha 1 and beta 1 are 2 paths, why is that not a generalized cycle anymore? So alpha 1 gamma 2 is disjoint from beta 1 gamma 2. So there's no extension of alpha 1 gamma 2 that can possibly extend beta 1. Let's see, so sorry, we don't need this. I'll write it this way. So if you follow alpha 1 with gamma 2, then that does not have a common extension with beta 1. So that alpha 1, beta 1 is no longer a generalized cycle in this example. Okay, so now let me just tell you what the conclusion of our whole business is the following theorem. The C-star algebra of this example is actually Morita equivalent to a continued fraction AF algebra, an F-Roshan algebra, for some irrational number in the unit interval. And of course, this whole thing depends upon the sequence K1, K2, K3 that tells you how many edges you put between successive vertices. And so it's really the correspondence between the irrational number and that sequence is a bijective correspondence. And what we felt was remarkable about getting this example is that while this is an AF algebra, it's presented as the C-star algebra of a groupoid that is not AF. So in fact, the groupoid has isotropy. So it's very hard to see where the AF structure comes from. We haven't been able to write it as a closure of an increasing union of finite dimensional subalgebras. So the proof requires the powerful classification result that's been proved in just the last few years. Let's see, so how am I doing for time?
Well, you still have 47 minutes.
Okay, so I still may not even use it all. Let's see what happens. Okay, so now I want to try to describe to you why this theorem is true by working through the construction of the C-star algebra from these examples. So one of the features of, yes.
So gamma star is something like similar to the ultra filters or the infinite path space?
Yes. So in general, working with a category of paths, you look at ultra filters in the ring of sets generated by these principal left ideals, I guess is the right terminology. And this doesn't require finite alignment to work with. It's just the presentation I'm giving here with these directed hereditary sets is a simplification that's possible because of finite alignment. Yes, the fundamental construction.
Infinite paths is like it.
Sorry?
So infinite paths is like.
So this is a really good point that I forgot to mention. So people would often like to think of these directed hereditary sets as being like infinite paths in this graph. And the problem is that two infinite paths might be representing the same element because of the identifications. So a more fundamental way of describing it is the finite, well, sorry, not finite, the directed hereditary sets. Actually, what I'm about to mention now is a way of describing these by infinite paths. And it's a bit, yeah, this actually is true in any category of paths. Well, when you amalgamate several categories of paths, every element has a unique, what I call normal form. So you can write it as a concatenation like this, where the elements are drawn from one or the other of your two pieces that you're amalgamating. And you do this in such a way that successive ones belong to the opposite piece. So let's just come back here for a moment. So we might take up a path in lambda 1, and then a path in lambda 2, then a path in lambda 1. And these pieces are uniquely determined. Now, within a piece, there's several ways to write it, right? So alpha 1, beta 2 is the same as beta 1, alpha 2. So we think of it as an element in one or the other of these categories of paths, but the sequence of elements is uniquely determined.
So you say like for one graph there is no such thing happening as an identification, but for higher rank graphs there is. So that's right. Why infinite graphs, infinite paths is like maybe not a good choice to think about this, but rather as a hereditary directed. So like filters, right?
Yes. Yes.
Okay.
That's right. That's exactly right. It's one graphs are very special because everything can be done in terms of uniquely represented as infinite words. But there's, when you know, like in this example, it's not as complicated because we understand how alphas and betas work together. But in the general situation, since you just don't know how to write things down as infinite words in a convenient way.
So what about taking ultrafilters?
Yes, ultrafilters is a good way of doing it. So I think the directed hereditary sets are easier to identify in an example. So having that characterization of the ultrafilters is a useful tool.
So like,
when I wrote this stuff up originally, I did it in terms of ultrafilters.
I see. Yeah, thanks.
No, you're welcome. No, it's a good question. You know, I'm trying to skip over a lot, as it turns out. So let's see. So in this lemma, I'm just indicating if you have two elements of lambda, when do they have a common extension? So we have to compare their normal forms. And it turns out that they have a common extension if and only if the normal forms agree, except possibly for the last term of the shorter one. And you have to have some compatibility in that last term. So maybe this is maybe a little bit more detailed than I need to talk about. But for example, these two paths have a common extension. The common extension is alpha gamma 2, or whatever edge gamma 2 you like, alpha beta, because that's the same as alpha gamma 2 beta alpha. So we have both of our original paths are extended by this one element. Okay, so you see they have the same first piece of the normal form and the same second piece, the gamma parts. The third piece are different, but they have a common extension in lambda 1 where they both live, so the whole things have a common extension. On the other hand, here's an example where if we put gamma 4 after the alpha gamma beta, then there's impossible to find a common extension with this other one because there's no way to adjust this beta by having something go further. And if you try to put a beta in here, you'll never be able to get the gamma 4 next to it. So that's just some trying to, again, illustrate what I was describing before. So now the infinite elements, the infinite directed hereditary sets come in these three forms. Maybe the third one is the most natural, where you have an infinite sequence, an infinite normal form. That would be the nicest example of an infinite path. So we just take longer and longer strings in this infinite normal form. But we might have something that's really just an infinite directed hereditary set in one or the other place that we are talking about. So this lambda infinity, the set of infinite directed hereditary sets, can be thought of in a way as infinite words in our category of paths. And then we can prove that those are exactly the boundary. So they're not all maximal, but the closure of the maximal elements gives us all of these. Oh, so here I tried to give some examples of boundary elements, so infinite directed hereditary sets. So here, the first one, so I have an element of lambda 1, an element of lambda 2, element of lambda 1, element lambda 2, and we keep alternating like that. This is really an infinite sequence of an infinite normal form, continually changing from one to the other of our two pieces in the amalgamation. Here we have an example that has some initial part and then an infinite element from lambda 1. And here we have an initial part and then an infinite element from lambda 2. So here we have really an infinite path in the one graph, lambda 2. Okay. Now, as I mentioned before, we restrict to the boundary. I'm not sure why I wrote this sentence. This is the description of G of lambda, but the restriction to the boundary just means that X should be taken from this boundary of lambda instead of an arbitrary directed hereditary set. You know, let me just quickly look at our picture again. So each vertex is a place where we could begin our paths. So there's really sort of a countable family of sets, all the directed hereditary sets whose range is a given vertex. And since you can move between vertices with various paths, those give us equivalent things. So in fact, if we look at things that start at the first vertex, that's actually a transversal in the sense of Muley, Renault, and Williams. So if we restrict just to those elements of the boundary, we get something Morita equivalent to the whole thing. So that's what I call the groupoid G. It's the restriction to this compact open subset of the boundary. And that's the groupoid whose C-star algebra is the F-Roschen algebra. Oops. Okay, and now, as I mentioned, this groupoid has isotropy, and here's where it comes from. So we look at this element C, where our first two factors or coordinates in the triple are alpha and beta, and then we have infinitely many alphas and betas after that. So this is the example we saw earlier that has the same source and range, namely alpha infinity, beta infinity, but it's not a unit. So the isotropy at this point, well, this generates the isotropy at this point, the common range and source. So the isotropy there is infinite cyclic. And in general, these are the points of X that have non-trivial isotropy, always isomorphic to the integers. So it's not a principal groupoid, but it is topologically principal. So this family of elements having non-trivial isotropy is countable and nowhere dense. And it's easy to see that it's a minimal groupoid. So the reduced C-star algebra is a simple C-star algebra. And it turns out that it does have an inductive limit decomposition, just not by finite dimensional subalgebras. So let me show you what the decomposition is. So we look at triples where the first two coordinates have bounded length. So for the ith subgroupoid, we restrict those to have length I. So if you remember our picture of swapping the beginning of an infinite path, in G sub I, we're only allowed to swap a beginning of length at most I. These three elements are typical elements in G sub I, because the beginnings all have length less than or equal to I. So if the length of mu is L, which is less than or equal to I, then our first two coordinates in all three of these are of that type. But if we multiply these together, we get something that has longer coordinates. And so to identify those, we have this lemma. All that you can really do, so you can have initial pieces of these first two coordinates of length at most I, and then you can adjust with some alphas and betas afterwards. So the first two coordinates are not arbitrary anymore. They're only arbitrary up to the ith coordinate, and then they have to belong to the lambda 2. So GI is actually a fairly small subgroupoid. And we do get an inductive limit decomposition in this way. So let me just point that out here. So if we look at the C-star algebras of the GIs, those form an inductive system for C star of G. Now the GI is not minimal, so we have some hope of understanding it. So the unit space we can, so the unit space of the whole thing, now we could decompose in the units in GI in this way. So we look at those elements that after the ith coordinate, it belongs to the first of our pieces, namely only with alphas and betas. And that's a closed GI invariant subset. So we get an exact sequence for the C-star algebra of GI in this way. Now this set Fi, so you should think of the mu as having only finitely many choices. All the elements of length less than or equal to I. And the X has to belong to lambda 1 infinity. So that's one of these types, either alpha to the P, beta infinity, right? So.
But your length is all the time multidimensional, right?
No, the I is an integer.
But isn't the mu in a higher rank graph?
Let's see, so no, the mu is in lambda, right? So let's come back to our picture of lambda. So mu is something in here, but our length is still the number of edges.
Okay. Okay.
So yeah, there's no natural degree functor. Well, we have this length, number of edges, but it's not so
okay.
natural. Yeah.
Thanks.
Let's see, where was I? Very hard to know. So X is either the form, alpha, I guess I need to write alpha to the P, beta infinity, or alpha to the infinity, beta to the Q, or alpha infinity, beta infinity, right? There are only a few choices for what we have as the X, and only finitely many choices for mu. So the whole set Fi is a countable closed invariant set. So it's actually quite easy to sort out what this C-star algebra is. And I think that's the next thing. So within there, we can look at just the things that end in this alpha infinity, beta infinity. That's also a closed subset. So we actually get an exact sequence for this quotient. So the quotient here is itself the middle of an exact sequence. It's an extension of essentially continuous functions on the circle by compacts, direct sum compacts, with some matrix algebra put in there. So it's an elementary, not quite elementary, it's a two-step type 1 C-star algebra. So in fact, the GI on Fi is an amenable groupoid. C-star algebra is type 1. We can compute the K-theory. So the K0 group is Z squared and the K1 group is trivial. So that's just that's a calculation using the 6-term exact sequence. Now, the complement of Fi is I called UI. So if Fi is the stuff that at some point it becomes entirely in lambda 1, the complement is stuff that is never entirely in lambda 1. So infinitely many edges are drawn from lambda 2. So maybe I won't belabor this construction, but we can decompose UI into the things, where the lambda 2 edges first start appearing. And maybe the takeaway in this slide is this formula for the C-star algebra of the restriction to U sub I. It's a direct sum of matrix algebras over continuous functions on a Cantor space, which is just the portion of our space X starting at a particular vertex V sub L plus 1. So this is actually a type 1 AF algebra. And so our exact sequence, let's see, where was it? So now we know that this is type 1, and this is type 1 and AF. So the C-star algebra of G sub I is really not so bad. Right? So here we have an extension of the circle by compacts. Here we have a direct sum of matrices over continuous functions on Cantor sets. So, well, we can work out what goes on with this one. So in fact, GI is amenable. So there's no confusion about full versus reduced C-star algebras, and they're nuclear. But G is the inductive limit of the G sub I. So G is also amenable. So all C-star algebras we're talking about here are nuclear C-star algebras.
Jack, there is a question about amenability. Alex, go ahead.
Let's see.
Alex has asked a question in chat.
Yeah.
Can you tell again how we derive that V's are amenable? Can you be more specific? Alex, I don't see what you mean by V's.
Yeah, sorry, you meant like that from these we get that GIs are amenable?
Yeah, so let's see. So it felt so elementary that I was I think that let's see. So I think that it's I believe there's this theorem that if the reduced C-star algebra of a Hausdorff-Étale groupoid is nuclear, then the groupoid must be amenable.
Yeah. Okay, I see. So it's
yeah.
AF.
So you're right to call me in this one. It's the C-stars that are clearly nuclear, and I think the amenability of the groupoids comes from that.
Yes, I see. Thanks.
And I have a question about this slide with K-theory. So can you identify the generators of K0?
Yes, I'm going to show you what they are in just a moment.
Okay, perfect.
Let's see. So the last comment on this slide is so we're going to use the classification theorem. And so we have to check all the hypotheses. And in fact, because of the elementary nature of these C-star algebras, these extensions, the the nuclear dimension has to be finite for these C-star algebras. So in fact, we can tick all the boxes for C-star of G. It's classifiable by this recent classification theorem. And so the question is to identify the Elliott invariant in order to know what C-star algebra we have. So yeah, we were forced to use the biggest gun in the closet in order to actually finish our theorem. Okay, so let me just mention, continue on with the K-theory of C-star of the GIs, these building blocks. So the K1 group is trivial, and the K0 group is really a direct sum of two pieces. On the one hand, there's Z squared, which is really coming from that quotient that we had before, and the Fi, and the UI gives us this direct sum of continuous functions from Cantor sets into the integers. That's the K0 group for the type 1 AF algebra that I talked about before. Now, it turns out the important part is the Z squared part, the Ni. So it turns out that the inclusion from one level to another maps the Ni injectively into the other Ni plus 1. So the Ni's form their own sort of coherent subsequence in the inductive limit. And for every I, there's a larger index I prime so that the Mi part gets pushed into the Ni prime part. So in fact, all we need in order to understand the K-theory of C-star of G is just what happens to these Z squared pieces that map along. And now we need the generators of the K0 group, and here they are. So we should be looking at this set in the unit space. So this is all the paths that begin with alpha to the I edges labeled alpha, but do not begin with alpha to the I beta. So you can find I copies of alpha at the beginning of your path, but you can't find a beta after them until you've been blocked by at least one edge labeled gamma. And here we have things that have I plus 1 betas at the end. So these are somehow the two basic kinds of compact open sets that we need. And what I mentioned before, this fact means that in fact the K0 group of C star G is the limit of just the Ni pieces. Okay, now to get from one stage to the next, we have this calculation. This is really ugly looking. Let me point out what it's saying. So here we have paths that begin with alpha to the I, but the I plus first edge is not a beta. That means it might be a gamma, or it might be another alpha, in which case you can't have a beta after that, or you could have moved it forward and violated this restriction. And now things that begin with alpha to the I gamma, well, they might have a beta afterwards, or they might not. So we divide that into these two pieces. And the result here is that if you look at what this is, we have a word of length I plus 1 minus a cylinder set for a word of length I plus 2. All of those are equivalent as under the dynamic, so as elements of K0. And similarly, this this other cylinder set is a union of two pieces that look in the same form. So it tells us that if we look at this generator, taking alpha I minus alpha I beta, in the next level, we have Ki plus 1, and then one more of this first kind of cylinder set. And we have, well, here are Ki plus 1 of the second kind. So these formulas tell us how those generators of K0 push forward into the next K0 group. And the summary is that this matrix B sub I built from ki plus 1 this way tells us how that happens. And so here I've summarized this in this diagram. So across the top, we have the sequence of z squared sum ends of the k0 group in C star gi. And on the bottom, there are z squared that they're isomorphic to. And the maps between them are really modeled by this sequence BIs. Now, if you notice BI, it's an integer matrix with determinant 1, so GL2Z. Now, the last ingredient is this theorem. This theorem is actually not trivial. If you look at this n sub I, say n sub 1, we know it's isomorphic to z squared, but it is part of the k0 group of a certain C star algebra. What part of this is in the positive cone of k0? So it turns out that it's exactly corresponding to the usual positive cone in z squared. So these are really the simplicial positive ordered groups, z squared with n squared, all the way along the bottom. So this inductive limit is exactly giving us a dicyclic dimension group. So it's what Efros and Shen studied in their paper. So this ordered group of k0 of g really is an the dimension group of an Efros-Shen AF algebra. Okay, so let's identify what Efros-Shen algebra it is. And I realize I'm almost out of time. No,
you still have.
Yeah, no, there's this funny thing with
minutes.
Zoom. Zoom freezes your clock at some preordained time. And so if you're looking in the wrong place, you won't know what's going on. Okay, so this is the usual notation for a continued fraction. The integer part of our number could be any integer, but after that, we insist that we have non-negative integers here. It's called a simple continued fraction if the later coefficients are all strictly positive. So now remember the sequence ki that defines which example we're looking at. That tells us how many edges between a pair of vertices we have in the one graph lambda 2. So if we look at that sequence, let's rewrite it in the following form. This is a little bit odd to look at, but C0 will be whatever K2 was. And now, the KIs might be 0. So we let C1 be one more than however many zeros there are between, there are following K2. So starting with K3, count how many zeros you have until you get a non-zero term in this sequence. Though that add 1 to that, and we call that C sub 1. And then C sub 2 is the next entry, that non-zero entry there. So in this way, we build a sequence of non-zero positive integers, C1, C2, C3. And that's where the continued fraction comes from that we want. So it's a very strange correspondence between the sequence defining our graph and the continued fraction that comes out of it.
And why do we ignore K1? Why is K1 so irrelevant for this continued fraction?
It's very strange, isn't it? This is what happens. But K1 comes back in at the end, and I'll show you that. Yeah, so again, this was so mysterious to us. It took us a long time just to even decide that we weren't making a mistake, because everything seems so bizarre. Okay, so let's let sigma be the irrational number we get from this continued fraction. And then P sigma is the usual thing, ordered pairs of integers that give us a non-negative number when combined with sigma in this way. So that's the positive cone in the corresponding continued fraction algebra. And now let's see, so coming back to this picture, how do we identify the positive cone? As we look at the usual positive cone in each of these, and we pull them back to the first place by using the inverses of these matrices. So we essentially pull everything back to the initial R squared containing Z squared in order to see what happens. So that's this construction. And it turns out that when you pull everything back, you get exactly P sigma. So the ordered K theory, together with position of unit for our C-star algebra, is isomorphic to this one. And here you see K1 shows up in the position of the unit in this strange way. Okay, so that's almost everything in the Elliott invariant. What's left is the pairing of the tracial states with the K0 group. So here we need to talk a little bit about what goes on there. So let's let E be the usual canonical, I guess that's redundant, the canonical conditional expectation from the C-star algebra of the groupoid onto the continuous functions of its unit space, right? X is the unit space of G. So in order to obtain a tracial state, the most direct way is to compose this expectation with a trace on C of X, but it should be compatible with G. So we use an invariant probability measure on the unit space and compose the conditional expectation with integration against that measure. So again, just recalling the definition, probability measure on the unit space is invariant if it has the same, assigns the same measure to the source and range of a bisection. Okay, I mean, a little bit technical groupoid stuff, let's not worry about it. So in our case, we proved this theorem. I'm going to show you a little bit about that in a minute. So our groupoid G admits a unique invariant probability measure on the unit space. Now, because of the structure of the groupoid, there's a theorem. Actually, the form we need, it's really due to results of Laka, Larson, and Nishveyev. But Nishveyev then wrote a separate paper with a more general result that we can actually cite. So in our case, every trace on the C-star algebra does factor through E. And so the traces are in one-to-one correspondence with invariant probability measures on the unit space. And from this, we'll know that the trace we're getting is the only one. So our C-star algebra has a unique trace. Let me just show you where this uniqueness of the trace comes from. So let's go back to these generators for the Z squared component of the K theory of the ith stage in our inductive limit. Right? So we had these characteristic functions of cylinder sets or a difference of cylinder sets, giving us K0 elements. So let's apply, suppose we had an invariant measure, what would it have to be? Let's apply the measure to these sets. So I'm going to call those AI and BI. So in particular, A0 is just the measure of all the things that don't begin with beta. And B0 is the one minus that, everything that does. And that's because we have a decomposition of X this way. And now, if you remember this ugly calculation I showed you, what I was mentioning is that these sets that look like differences, since they always have the same length of paths involved in them, they have the same measure by invariance. So we get this formula relating the measures of these sets from one level to the next. And we can summarize it this way. It's that matrix BI, capital BI, that connects one to the next. In particular, at the first level, we get this relation between the A1, B1 and A0, B0. But A1 and B1 are measures of sets. They must be non-negative. So these two quantities must be non-negative. And if you write down what that means, you get this pair of inequalities for A0. Remember what was A0? A0 was just the measure of this specific set in X. All the directed hereditary sets that don't contain the element beta or beta 1. Okay, so if we write it in the notation for continued fractions, it looks like this. And now let me just say that if you apply the B1 inverse, B2 inverse, you can get a similar kind of inequality for every n. And this tells us that A0 is determined by the sequence Ki. So that A0 has to be the measure of this set, and it has to be given by this infinite continued fraction. So that's the number that we call theta. Now, it's true that the Ki's don't all have to be non-zero, but since infinitely many of them are non-zero, this is actually a well-defined continued fraction. And we do get this irrational number theta. Because this the integer part is 0, theta is between 0 and 1. Well, we already know that. It's the measure of a subset under a probability measure. So it's between 0 and 1. Now, remember the, let's see, so AIs are gotten from previous ones using the BIs, which are GL2Z matrices. So all of these elements are AI and BI are integer combinations of A0 and 1. So they're all in Z theta plus Z. So mu is completely determined on the base for the topology. And so it's completely determined. And this is how you can prove uniqueness of this measure. Now, because this uniqueness theorem gives you, in some sense, an explicit formula for the measure of these sets in the base for the topology, we can turn it around and prove that those formulas really do define an invariant measure. And that's the existence proof. Well, so I'm almost finished. So the last ingredient is coming back to this diagram that we had before. So again, the K1, the first index, little k1, only seemed to enter into the position of the unit when we stopped here. But if we apply B0 and then this extra element, let's see, where's theta? This is where the extra elements come from. So if we want to use this entire continued fraction, we need to use this full sequence. And that tells us that we have an isomorphism from what we had before as the ordered K-theory to the standard ordered K-theory for the irrational number theta. And that finishes the proof that, in fact, the C-star algebra we have is the continued fraction AF algebra. Well, that's it. I'm going to stop there.
Okay.
So thanks for asking questions along the way.
Yeah, we'll continue. Let's clap hands first. Let's thank Jack for a beautiful talk. Thank you so much. And now we still have plenty of time for questions. Before I pass my voice to, I give somebody else an opportunity to ask a question. I have just a silly technical question, Jack. Could you go back to the slide with the generators of K0?
Yeah, let's find it.
So we're explaining the cylindrical sets and so on. Yeah, but there is not, yeah, okay, chi. So what do you mean by chi labeled by a subset?
Okay, so let's say, so Z of, say, alpha is a subset of X, right?
Yeah.
X is the unit space of our groupoid, right?
Mm-hmm.
So the characteristic, it's compact open, right? So the characteristic function of Z of alpha is a continuous function of compact support on X.
Okay, so it's
but of course that's,
mm-hmm.
Yeah, so it's a continuous function of compact support on G. So it determines an element of the groupoid C-star algebra. So that's the sense in which I use the chi, the characteristic function.
I think you didn't mention it, and
I didn't, and yeah, there's so many of these things that become second nature.
Yeah.
When you're working on something, you forget that it's unfamiliar.
All right. So, anybody else? Any more serious questions? Please go ahead. Fire at will.
Yes. So I have a suggestion from like some slides before where you. So can you hear me?
Yeah,
Yes.
we can hear you.
Okay. So some slides before, like you introduced like some way like to construct a groupoid, and when you did so along the way, I mean, like you basically considered pairs of finite paths, right?
Yes.
And then with this and then modding out some relation
Right.
that actually could be handled. For example, I was doing this for one graph, but I guess this could be handled like in your case as well, like for a higher rank graphs or for categories. It's like the inverse semigroup is acting on a space, and what you then like how you obtain this modding out relation is by the germ groupoid, as a germ groupoid of your transformation groupoid.
Yeah. Yeah. So I know what you mean. Yes, that can be done. In the case of the categories of paths, you do get the same result.
Yes,
So
because
I since had had the occasion to the need to generalize this construction a bit further. So in fact, as I mentioned, it's really only the left cancellation that's necessary to make this process go and build a C-star algebra. If you do that, so say just with left cancellative small categories, then there are some problems when you use the groupoid of germs. And it turns out that sometimes you need something a little bit different.
So can you explain what kind of problems?
Let's see, do I remember? It's been a while since I wrote this down. Well, it has to do with having inverses. So one of the examples, if you have if your small category is actually a discrete group, then this construction with germs collapses everything and there's nothing left. But if you hang on to a bit more structure, you can actually get the group C-star algebra as get the group itself as your groupoid. But you can hang on to a bit of what's there. And so you can imagine that in a left cancellative small category, there might be some places where there are inverses and others without. And so the germ approach to the groupoid will sometimes collapse some information that you can hang on to with a slightly different construction.
But when you go back to the slides, like of your construction.
Yeah, let me find it. It's
and the way you mod out, like exactly. So
right here.
What I meant is that basically this looks like what you're doing is nothing but you're taking the inverse semigroup freely generated by your category, like lambda times lambda, and let this act on the, let's say this space, this topological space that you got, like lambda star. And it acts like this is a representation of your inverse semigroup. And what you can then take is simply the germ groupoid, and this is exactly like the relation that you're modeling out.
Yes, I think that's true. What I was trying to make an excuse. The construction I've given can be generalized in a situation where the germ groupoid gives something different. But in this context, for the categories of paths, it does give the same result. Yeah. So in fact, here I'm still sort of, this is maybe a problem I have from my original motivation or intuition in looking at this, is trying to think of these as kind of paths, and the swapping of the beginning. I'm really hanging on to that intuition, and that is more apparent in this approach as opposed to the action of the inverse semigroup. Yes, but you're right that and I think maybe Alan Danzig and Milan were the first ones to point out to me, amongst many other people who have since done it, that it's maybe more efficient to go at this from the point of view of inverse semigroups.
Exactly. Also, like in the way like Excel does. I mean, like I guess like you're doing similar things like Excel does in his combinatorial C-Algebras paper. Like,
say it again. I missed the last.
I mean, I guess you're doing quite similar. You're going a quite similar route, like Excel's combinatorial C-Algebras paper.
Yeah. So the combinatorial. Well, there is no paper yet, though. We're going to write. We're almost finished with this one, but yeah. So I think like from directed graphs, higher rank graphs. Categories of paths, left cancel of small categories. These are the kinds of oriented combinatorial data I'm thinking of.
Yeah, and I got also like another point, like so in the usual Diacono Renault groupoid that one constructs from ordinary one graphs. One also has this copy of the integers encoded in the groupoid, right? I mean, like one has like these.
Right. That's the length function.
Exactly. I mean, like so when one runs this argument, this construction, it can happen that one loses this information along this construction. So if you take, for example, like if you take a graph with only one loop, and then it could possibly get lost like along the way. Right.
So this is the I think this goes back to the first papers on graph algebras, is using this. The triples they use are two infinite paths and an integer, giving you you want sort of shift equivalence of infinite paths with lag, and you have to keep track of the lag exactly because of these points that have isotropy, which is integer isotropy, they shift them out. So what's going on here by using this other kind of triples, there's only one infinite path and two different beginnings. So you might say the lag is caught in the difference of length of the two first coordinates.
So if you have it's not covered in the length of the two. I mean, like it's covered in the length, but as soon as one mods out, then this information could possibly get lost.
No, the difference is preserved. The difference in length is preserved by the equivalence relation. But in any case, the point in this more general context is that for a category of paths, there may be no analog of length function. There may not be any homomorphism into the integers at all. So there's no integer that present to be able to use for this purpose, and you have to do something. Yeah. You can't really use that integer coordinate the way you could with higher rank graphs. It's a k-tuple of integers, which is playing the same role, but that just isn't present in general for this more general situation.
So does one always recover always recover the original graph algebra?
Yes. So for higher rank graphs, this construction gives the exact same result. And in fact, there's a characterization of these C-star algebras by generators and relations, and it looks very much like the one given for higher rank graphs. And in fact, it's exactly that if you start with a higher rank graph.
So where is this length function encoded, or how is this length function encoded?
So if you look at your higher rank graph as a category of paths and build the C-star algebra, so where would we find the degree functor? Well, from a category of paths, you can look for homomorphisms into abelian groups or abelian monoids. And if there's a homomorphism into nk for some k that satisfies the unique factorization property, then you know you have a higher rank graph. So if you're just given abstractly a small category, a category of paths, how do you decide if it's actually a higher rank graph? Well, you have to look for this degree functor with the right property. And if you can find it, then you know you have it, but it's not intrinsic. I guess this is maybe the point I'm making, is that the degree functor is not intrinsic to the situation. You know, actually, I don't know if there might be two completely different degree functors on the same small category that both satisfy unique factorization. I don't know if that's possible or not.
Okay, so the unique factorization, this is like encoded inside the category, and this gets like handed over like to the construction.
Yeah, so if you have it, you can use the K-graph, the higher rank graph theory construction, but even if you don't know what it is, you don't need it in order to build the same C-star algebra.
Yeah, thanks.
Yeah.
Anybody else? Tomek, no questions?
Maybe one question about this construction in the context of well-known groupoids. Let's say, for instance, if you have a graph in the topological sense, one-dimensional complex, CW complex, let's say, then you can speak about the fundamental groupoid.
Right.
You can generate a groupoid algebra from this. Is there a relation between this construction and the previous one?
I don't think so. So the fundamental groupoid, this is a countable groupoid. So it's, you know, so it certainly has the discrete topology is reasonable. It's not the kind of groupoid that is typically of interest in constructing C-star algebras. You know, you get something that's not so, well, it's a discrete kind of thing. Like if it was just a group, you would have a group C-star algebra. That's very interesting, but it's not sort of in the same philosophy as these results. If you have a graph, this is non-oriented combinatorial data. And so it's a different kind of animal in a way. Yes, I would say it's in that sense, it's very unclear to me how this might relate, because I found this dichotomy between oriented and non-oriented data going into a construction of a C-star algebra to be profoundly different. I'm not sure if I'm interpreting your question properly.
Mm-hmm. So you started your talk with evoking combinatorial constructions. So usually in combinatorics, people start with non-oriented graphs and things like this.
Right.
So there is. So you say that there's no relation between this construction and other constructions.
Well, okay, so no, okay, now let me back off. So I began by saying I wanted to talk about oriented combinatorial data. Now, if you take a directed graph and forget the direction, or just take a graph that, as you said, a graph without a direction. So people have defined the C-star algebra for this. I think it's Corneliussen, someone who can't remember, Marcoli, have a paper about the C-star algebras of just graphs, not with a direction, and computing the the Beatty number of the graph in terms of the K theory for something associated. And it turned, I know David Pask has made a detailed study of this situation. So the C-star algebras you get from graphs without a direction are a very, very small subset of the kind of C-star algebras you get from directed graphs. So the difference between the oriented and unoriented case is quite big. The kinds of C-star algebras you get are there are far fewer algebras you get from the unoriented case, but it's a different kind of question that they were asking in this paper that was relevant for the unoriented case as opposed to the oriented case. Another example is, so this is some work I did with several people in Australia. If you have a graph of groups, then you can build a tree, undirected tree, and you get a boundary for an undirected tree, and the fundamental group acts on this boundary, and you can discuss that dynamical systems C-star algebra. So that's again related to an unoriented, maybe a kind of unoriented combinatorial information. And it seems very different from the kind of things you get from the oriented case.
What about introducing some orientations coming from, for instance, some actions, like in Cayley graphs? Isn't it a bridge between these two worlds?
So, well, so if you have a Cayley graph for a group, for example, you know, in a way, it's so every edge is really two edges, right? Because you have the generator and its inverse. So if you have a non-symmetric generating set, then maybe you're actually defining a monoid within your group. And then you get a oriented graph, but it's really more related to the C-star algebra of the monoid rather than the C-star algebra of the group. So that's really been an example of Lee's semigroup C-star algebra construction. That's one way, but your point is a good one. I don't know in what sense the Cayley graph. Yeah, so if you have say a Cayley graph for a group given by a non-symmetric generating set, my feeling is that you'd be looking at a kind of monoid C-star algebra, which would be of the kind I'm talking about. But I'm not sure there aren't other ways to interpret that. I don't know a good answer to your question.
I was asking this question because this boundary type of thinking, this one-sided path going to infinity, right. It reminds me this Gromov construction of the boundary of a group coming from the Cayley graph. So okay.
Yeah, it's very interesting. I don't really know how to fit the Gromov boundary into this framework. So the one result of this construction is that you always get a totally disconnected boundary, where there are many interesting groups where the Gromov boundary, of course, is connected.
Yes.
So this is giving you a kind of disconnection of that boundary.
Mm-hmm. Okay, so you said that this boundary action is topological principal and minimal.
Yes. For these examples.
In these examples.
Yes.
What can happen in general? What about the quotient of this boundary by this action? Or can be this action non-principal in general? Topological non-principal?
Yes. So with a minimal action, of course, you probably don't want to take the quotient. Yeah. But the action might not be minimal. It might have some more structure. Yes, in general, I don't. The examples are wide open. The categories of paths are really very general, and so there's all kinds of things that can happen. So we were focused on this particular examples heading toward a certain kind of C-star algebra at the end. But so for us, it was important that it turned out to be minimal and topologically principal. But that's certainly not a given in this context.
Can I ask one question more?
Sure.
It's maybe too general. It's a question about properties of this functor associating with every groupoid sister algebra. Are there some general categorical properties of this functor, like transporting some sums of these groupoids into some construction on sister algebras?
Sums, so a disjoint union of groupoids would certainly go to a direct sum of sister algebras.
What about other?
I don't know. I don't know. I have to say I'm ignorant.
Mm-hmm. So no easy theorems about some kind of additive structure in the sense of some simple modifications of the graph producing on the level of sister algebras something like pullbacks or something like this.
Yeah, no, there is some things known about pullbacks. So Piotr did some work with
yes, so I asked
pullbacks. Yeah. So with one of my students, we've generalized this a bit. We're in the process of writing that up. That's for the case of directed graphs, not for the more general categories situation. But I think it's quite tricky. I don't know any general results.
So passing from graphs to categories doesn't help much.
It makes things much more complicated.
Even
in this context,
okay.
I think. Yeah, I don't.
Yeah.
So it's harder there.
And can you elaborate on this generalization you just mentioned in the passing?
Oh well, so you remember a few years ago you came to ASU and gave a talk on the preprint you guys had, and so we decided that we would do the non-row finite case, and it's it wasn't so hard, but it sort of is blown itself up into a little bit more of a well, I think it's an interesting generalization. Yeah, so it sort of fell by the wayside in recent months because I was doing this other thing, but we will try to finish this up. Let's see. So
I'm asking because in the final published version, and I have all co-authors here, Sarah is around and Mariusz is around, that in the published version, we also did it without the assumption of row finite.
Oh, I haven't seen that. So we'll have to look and see if we actually have anything to add now. Thank you for telling me.
Yeah, and you know, but it was kind of forced on us by a referee report of another paper, also on graphs. And the thing is that simply there is a theorem. Is Wojtek still around? Wojtek Szymański? No, he's already gone. But there is a theorem of Robertson and Szymański, and we just realized that if we stick to the row finite case, that basically our theorem is a special case. Oh yes, Sarah is right that we neglected to put the final version on the archive, but it's freely available. It's gold access. It's freely available at the Banach Center. So the published version is without unrestricted access. At the Banach Center pages. So we realized that in fact, in order for our paper to have any meaning, not to be just a special case of Robertson-Szymański theorem from, I don't know, 10 years earlier, we realized that we have to go beyond row finite, because somehow in this generality of Robertson-Szymański, where we're using correspondences, they were row finite. This was assumed, there for very more general setting. And we realized that simply the proof goes basically the same way. You just have to be a little bit more careful. We realized that it's actually that our mistake was that we cited a more specialized theorem, but in fact our proof remains intact for things that are not row finite if we use a more general lemma published by somewhere else. So that was the only thing that we had to take care of. So we fixed it already with Galli proofs. So this was but we didn't realize it until we got a referee report on another paper which mentioned Robertson-Szymański. When we looked up this paper and said, wait a second, I mean, if we're non-row finite, then we're just a special case of an old paper. Anyway, that's removing row finite turned out to be very, very simple, and I'm wondering why we didn't somehow notice it earlier, because it was one of the points of debate, I think, with Aidan Sims, who contacted us immediately after we put our paper on the archive, because somehow the different, they're also working in the higher generality. They had this pullback like theorem for higher rank graphs. But if I remember correctly, the difference between our approaches was that they did not assume row finite, but they assumed that they have no sinks, whereas we never had any problems with sinks. But because of citing wrong lemma by somebody else, I mean, not general enough, we had this row finite. But now row finite is gone. That's
okay. Good.
Yeah. I can just send you the PDF
yeah.
copy of the published version right after the
okay,
session.
thanks. Yeah. So I just want to respond to one of Alex's comments. When you have in the non-row finite situation, this is why you have to include, say in the case of a graph, directed graph, you have to include the vertices with infinite valence in the unit space. And it doesn't violate the compactness versus local compactness. It's just what makes it locally compact at all. But I think that's not a problem. And when however you do this construction, you'll realize that those elements are put into your unit spaces, into the boundary as well. I haven't had a chance to read your longer question.
In chat.
Okay, yeah, so
yeah, I think he answered it.
I have to think about it a little bit more, yeah.
Okay, good. So if there are no other questions, let's thank Jack again. Anybody wants to ask a question? Well, I don't see any raised hands. So let me choose reactions, clapping hands. So thank you again. Thank you very much for a very exciting talk. And before I stop recording, let me advertise the next speaker. The next speaker is going to be Guoyang Yu from Texas. So for a change, we don't jump. Yes, Sarah is right. Yes, Sarah is right. Jack, please send me the slides, okay?
Yeah, I'll send them after this.
Yeah, exactly.
Oh, after breakfast. Yeah.
You mean after dinner? Okay. Yeah, we should go out for dinner now. I hope to see you there in a week. And for a change, we're not going to jump across the ocean. We just moved from Arizona to Texas, so it's the same sort of southern border, right? It's not a big move from Arizona to Texas, and it's also going to be K-theory. So I hope to see you there next week. For the time being, thank you very much. I stopped recording.